Statistics Unit 5, Lesson 1, Part 1, Average of one population. In this lesson, we want to estimate a population average and then find the sample size needed to get a confidence interval of a given width, just as we did for one proportion. So on this one, we have a quantitative variable, which has a population mean mu. A good point estimate is the sample mean x bar. If the variable itself has a normal mu sigma squared distribution, then the sampling distribution for the sample mean is also normal with the same mean and a variance of sigma squared divided by n, meaning the x bar values will actually be less spread out than the values in the population themselves because they're an average of n values. We can standardize that if we take x bar and subtract mu and divide by the standard deviation, which is sigma over the square root of n. That will have a standard normal distribution. Now, if sigma squared is unknown and you substitute the sample standard deviation instead of that, then instead of having a standard normal distribution, you actually have what's called a student's t, or just a t distribution with n-1 degrees of freedom. So having sigma unknown adds another source of unreliability, so the t distribution is a little bit more spread out than the standard normal is. When we collect that sample of n observations, we get n pieces of information, but because we had to estimate standard deviation for that, we ended up losing 1 degree of freedom. So the properties of a student's t is that it's symmetric with a mean of 0, just like the standard normal is. The standard deviation varies with the sample size, but it's always more than 1. So it's always more than the standard normal has. And as the sample size of n gets larger, the student's t distribution approaches the standard normal, meaning they will be almost the same. So if we start with a variable whose distribution is not normal, but we take a large enough sample, which is typically used as n is bigger than 30 as the rule of thumb, then a standard normal distribution would be a good approximation where the sigma squared is known or unknown by the central limit theorem. So if you know the population variance, you could use this. This was if the variable was normal, and now it's true that if we have a large sample, even if the variable started off not to be normal, it will still be approximately standard normal. If it was normal, it would be a t distribution if sigma was unknown, and if we have any kind of a variable and we have a large sample, even if we put an s, it will still be approximately standard normal if sigma squared is unknown. As the sample size increases, of course, the shape becomes closer and closer to a standard normal, even if the original distribution was very skewed or extreme outliers, but then n equals 30 wouldn't probably be enough. You would need a much larger sample to have that. So to find a confidence interval for mu now, we can do the same like we did for the proportion, and we would put the probability of missing the true average, which is alpha, into the two tails of the appropriate distribution. And now there's 4 cases to that. There's normal sigma squared known, normal sigma squared unknown. Of course, the ones with sigma squared unknown are unlikely. It's unlikely that you don't know mu, but you do know sigma squared, but I've listed them for completeness. The normal would be you know the variable is normal and sigma squared is unknown, or it's not normal and sigma squared is unknown, and then you need an n which is large, typically bigger than 30. You can get any of those using the Texas Instrument calculator. So you want x bar plus or minus the z1 minus alpha, and then if it's the sigma is unknown, it will be sigma over the square root of n. If it's s over the square root of n. They all have the standard normal value except for the one when it's normal and sigma squared is unknown. That will have a t 1 minus alpha over 2 with n minus 1. If n is small and it's normal, this is the one you would want to use. If n was large, this and this will be about the same thing. These are under stat test. There's option 7, which is for a z interval, so any one of these would be a z interval. And then this one is option 8, which is the t interval. These you would put sigma in when they ask for the sigma, and then this one, the calculator doesn't know whether you put in sigma or s, so for this one, when you want to substitute s, you would just put in s when they ask you for sigma. When we find our interval, we will be like for the proportion 1 minus alpha, 100% confident that mu is now contained in our interval. In this example, in a study of jujube fruit, 15 samples of ripe fruit were analyzed for their vitamin C content with a mean of 50.44 milligrams per 100 grams of pulp. Assuming that vitamin C contents are normally distributed with a standard deviation of 13, find a 90% confidence interval for the average vitamin C content of jujube fruit. So the variable is the vitamin C content, the population ripe jujube fruit, n equals 15. This is the sample mean, and then we were told that the variable vitamin C's are normally distributed with the standard deviation of this. Since this standard deviation comes from the distribution and not from the sample, that is the population standard deviation, which is 13. The alpha, 1 minus alpha is 0.9, so alpha is 0.1. You would go to Z interval and choose stats since we have no data. When it asks you for sigma, you would put in 13. When it asks for X bar, you would give it 50.44. You would put in the fact that this was from 15, and you would give the confidence interval, and it will calculate this value for you. Again, I want you to know the formula and how to find that value if you needed to, which you're going to use with the inverse normal by putting in 0.95, 0, and 1. But this will give you this number. Again, remember, this is assuming that the variable has a normal distribution with a known variance. Then this would be an appropriate confidence interval. And then we are 90% confident that the average vitamin C content of ripe jujube fruit is somewhere between 44.919 and 55.961 milligrams per 100 grams of pulp. In another example, it says, in a study on the chemical characteristics of bee honey, the pH of 13 samples of honey was measured, and we had the data. If the pH values of bee honey are normally distributed, find a 95% confidence interval for the average pH. So the variable is the pH, the population is bee honey. In this case, you would use option 8 for the T interval. Why? Because we have a small sample. In fact, we don't really know these yet. We would have to get that from this program. N is equal to 13. We don't know the standard deviation. It's not given in the question. It doesn't state it with the distribution. We are told that they're normal, so a T distribution is appropriate. We would use a T interval. Now we're going to select data. It's really the only difference. Our data needs to be entered in list 1 in statistics, and then we also have to specify the confidence interval. Then it will calculate these values for you. By the way, variable has a normal distribution with unknown variance. The confidence interval, X bar plus or minus T, 1 minus alpha over 2 with n minus 1 degrees of freedom. S over the square root of n, where you would look up this T value. You can actually find that by T inverse. You can go to distribution. You can go down here to inverse T. We want an area of 0.975 with 12 degrees of freedom. We would put that in there, and we would find that that T value is about 2.1788. There are also tables where you can read those numbers from, and the program would calculate that you would get 3.6601 and 3.9599, so we are 95% confident that the average pH of bee honey is between those two numbers. If we want to, like we did for the proportion, have a confidence interval of a certain width, we would take D as half of that desired width and choose our level of confidence. And then if we take the fact that D is half of that, we would have N needed is bigger than or equal to the table value for the Z squared times sigma squared over D squared, where we must start with an estimate of sigma. So you would have to have some idea about the variability in the population before you started. Suppose for a particular variable with variance of 10, it's to be measured for a large population. What sample size is needed to have a 95% confidence interval? This is now for the mean of width 2. 1 minus alpha is 0.95, so alpha is 0.05. You can get this Z value by the inverse normal, 1.96. And D is, you want a width of 2. You take that and divide by 2 as 1. Put that in the formula, and you will get 38.416. So we need a sample size of at least 39 to get a 95% confidence interval of width 2.